let's see. We covered an important theorem last time, and so I just want to sort of remind you. So here's where we left off. So we left off with. And so we'll see why this is so important eventually. But this, like I said last time, the theorem, I guess it was 2.5. Theorem 2.5 is in some sense the key to all of Galois theory, right? We will come back and we'll make use of that theorem in key moments. So we left off here. So if alpha is algebraic over K, and then we need a monomorphism I, so I from K to L. And remember, this alpha just lives in some extension of K, not necessarily L, right? Likely not L, right? Some place that contains K, though. So then we have, so this is a monomorphism. And then we need beta, so beta is some element of L. So if we have this for the setup, then there exists a unique extension, J, from K adjoin alpha to L, so an extension of I, if and only if, sorry, I gotta say such that J of alpha equals beta, if and only if beta is a root of the output of the minimal polynomial when you apply I to it. Okay? So, the picture, let me just sort of draw a diagram here. So here's K, and it's sitting inside some, right, there's alpha. Alpha lives out here, all right, but we can think of, here's K adjoin alpha. And then L, we've got L over here, and then beta is living over here. So then what did we have? So I, right, is a mapping from K to L, and then this theorem says that we can extend I to J in such a way that alpha goes to beta in a unique way. And so let's say it like this. So if say beta 1 through beta sub s, so if beta 1 up through beta sub s are the roots of I of m sub alpha in L, and there could be other roots of this polynomial right here, but the ones that live in L, right, so if this is the roots that live in L, then there exist, let's say it better than for each. Yeah, okay, so then for each 1 less than or equal to t less than or equal to s, there exists a unique extension let's say, what did I call it? J sub t, I think, yeah. Yeah, J sub t. From K adjoin alpha to L, such that J sub t of alpha equals beta sub t. And so it's really just a quick corollary, recognizing if you look at this observation right here, then, so we'll state this as a corollary to our theorem. So if I from K to L is a monomorphism, and alpha is algebraic over K, and I of M sub alpha has S distinct roots in L, then what? Well, from this observation here, we have exactly one extension for each of those, for each of the beta S's, right? So, then there exists exactly S extensions from K adjoin alpha into L of I. I'm not going to give them a name there. Right? There's exactly S extensions of I, right, from K adjoin alpha to L. All right, so there's nothing to prove. It's just this counting right here. Now, I thought the proof of theorem 2.5 was pretty fun. In fact, I thought that all of the proofs that we've done so far are fairly enjoyable. This next one, I don't know, the proof is just tough. The consequences of this theorem are fun, they're interesting, and we're going to prove those. But the proof of this theorem, I don't know, I find it, I'm not going to say unenjoyable, but you have to kind of keep your head straight and put everything in exactly the right spot and exactly the right order. So it's I'm not gonna say nerve-wracking, but it just takes. So my point is, we're gonna get through this, but I can't say that I'm gonna enjoy the next 5 minutes or whatever. So let's let sigma be a splitting field for F over K, and we need a monomorphism over K, and let I from K into sigma be a monomorphism. So now, sorry. No, I don't want sigma there. I want, right. I'm sorry, I need L here. Okay. So now this theorem is going to tell us when we can extend I to all of sigma. So, so then, there exists an extension little j, there exists an extension j from sigma to L if and only if I of F splits over L. So, I mean, if you think about our previous theorem, it allowed us to extend over K adjoint alpha, right, over a single root. And so now what this theorem is going to allow us to do is extend over the entire splitting field, right? If essentially all the roots live in L, right, then you can split, so that I of F splits, right, then you can extend it sort of one by one. You can extend, so K adjoint alpha 1, K adjoint alpha 2, K adjoint alpha 3, and so on. So root by root, you can extend. So, I mean, this is not, it's not particularly surprising. What it's just saying is, right, our previous theorem says, okay, you can extend it from k to k join alpha. And so if you had multiple roots, right, you could do it over k join alpha 1, alpha 2, and so on. And what do you need? Well, you just need all the roots of I of f to live inside L. Okay, but the proof is it's intricate. So and this is an if and only if statement. The forward direction actually is not difficult at all. So let's just write out f. So let's write f equal to c times x minus alpha 1 up through x minus alpha n. Right? We've got a splitting field, and so f can be expressed in this way. So here where c is in k and each alpha I, so alpha I lives in sigma. Okay, so now what do I need to do? Okay, so I'm trying to show we're going to the forward direction, so I need to show that I of f splits. So now, and we know that we have an extension, so we're assuming that we have this extension j. So we can say now, let's put it over here. So now, I of f, that's equal to j of f, because j extends I. Now, if I apply j to f, and here's the thing. Here's what's happening. So f lives in k bracket x, right? And so the coefficients of k, the coefficients of f live in k, and so we can apply I to each of the coefficients. The problem is I can't apply I to f in factored form, but I can apply j, right? So that's what's nice. So this is equal to j of f, which is equal to, well, it'll be I of c times x minus, I need a little room here, x minus alpha, j of alpha 1, x minus j of alpha n. And so what is this? Where does this happen? Right? Well, all of the j of alpha i's, those live in L, and so this, right? So this, we could say, so which is a splitting of I of f in, so this is happening in L bracket x, which is exactly what we need. We need I of f to split over L. So, okay, so now the hard direction, that's the reverse direction. So, and the proof is by induction. So this is induction on the degree of f. Okay, so for the base case, we consider if the degree of f equals 1. So if the degree of f equals 1, okay, so what does that mean? It means it's a linear polynomial, right? You can think of it as x minus alpha. So then we don't need to split, right? So then k is equal to sigma, and then there's no extension needed, right? Then j equals I. Right, we already have I going from k to L. Okay, so now we'll consider the situation where the degree of f is greater than 1. So now let's assume that the degree of f equals, let's say, n greater than 1, and that the result holds for any polynomial whose degree is strictly less than n. So let's say it holds for degree less than n. But let me actually spell out what that means. So I guess put a period here, and then I'll give a sort of clarifying sentence. So that is, let's say if degree, so that is, if the degree of G is strictly less than n, and I of G splits over L, then there exists an extension J from sigma to L of little I. And I just noticed I have a typo in my notes. Let me fix that real quick. Okay. So now what we're going to do is we're going to consider this polynomial right here, right? We're going to assume that I of f splits over L, and then we need to come up with an extension, right, of I from sigma into L. So so let's let C in K and alpha 1 through alpha n. In oh right, in sigma be such that f equals C x minus alpha 1 dot 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 up through x minus alpha n, right? We know that sigma is the splitting field for f over k. Now so now I want to just look at that first root. So now we have I want to look at the minimal polynomial. So m sub alpha 1. This has to divide. So this divides. And I should m sub alpha 1 here. This is of course happening in k bracket x. This divides f, and so right, and so well, okay, let me just say period there. So now since, so let's see what's happening here. M sub alpha 1 is just a polynomial with coefficients in k. But it's the minimal polynomial for alpha 1, right? So it's going to be a divisor of this polynomial right here. And now what I want to do is use the fact that sigma is a field, so sigma bracket x is a UFD. The unique factorization is going to tell us that m sub alpha 1 is going to look like, right, a product of some, I don't know how many, we don't know how many, but it's going to look like a product, right, of some of these factors right here. So since sigma bracket x is a UFD, we can assume, so we may assume without loss of generality, all right, that, just by reordering the terms here, that m sub alpha 1, it's going to take some of these factors, so it'll definitely have x minus alpha 1. And then, maybe or maybe not, x minus alpha 2 is a factor, is part of the factorization of the minimal polynomial. Well, if it wasn't, then reorder and push somebody else there. So that's where this, without loss of generality, is. Up to ordering, the factorization of m sub alpha 1 is going to be x minus alpha 1, x minus alpha 2, dot, 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 up to x minus alpha sub r for some r. And then I want to let G equal the rest of the stuff. So letting G equal C times x minus alpha to the r plus 1, dot, 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 up through x minus alpha to the n, we have that f is equal to m sub alpha times g. So what does that tell us? Now what I want to do is apply I to f, and then that would mean I can apply I on the right-hand side. So now I of f equals I of m sub alpha, I of g. And oh, sorry, that should be an alpha 1 there and an alpha 1 there. And let me just make sure I get all my pieces in the right order. Right. So we can say and since I of f, our assumption is that I of f splits over L, let's see, if I of f splits, that means that this product right here splits, and that tells us then that I of m sub alpha 1 splits over L. And so we can say, and since I of f splits over L, so does I of m sub alpha 1. And so what does that mean? So then, so we can say, and we know that m sub alpha 1, and therefore I of m sub alpha 1, it's a degree r polynomial. So what that means is there exists beta 1 up through beta r in L such that I of m alpha 1 equals x minus beta 1 up through x minus beta sub r. Now, since alpha 1 is algebraic over k, and I of m sub alpha of alpha 1 of I'm just gonna use beta 1. Doesn't matter who we use, but okay, let's use beta 1 equals 0. Right, here's m sub alpha 1. Beta 1 is a root of it. So since this equals to 0, there exists. So now I'm going to apply our previous theorem 2.5. So there exists a unique extension, and I'm going to call it J sub 1. So J sub 1, and it's going to go from K adjoin alpha 1 to L, such that, or this is of I, such that J sub 1 of alpha 1 is equal to beta 1. All right, so that is our theorem 2.5. Okay, now remember f, it's a polynomial in k bracket x. So its coefficients live in k, which means that its coefficients live in k adjoin alpha 1 as well. And so I can view f as a polynomial living in k adjoin alpha 1 bracket x. So let's say now view f as, or let's just say f element k adjoin alpha 1 bracket x. And so then, oh yeah, sorry, I want to keep going with my sentence here. So let's say, and write f equal to x minus alpha 1 times h, where h is also in k adjoin alpha 1 bracket x, right? Alpha 1 lives in here, so we know that we can pull off an x minus alpha 1. I'm just using the division algorithm there if you like, right? So now, we know that sigma is the splitting field for f over k, which means that h is going to split in sigma bracket x as well, and it's got to look exactly like the splitting of f, which means, so let's say note that h equals, well, it'll be c times x minus alpha 2 dot 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 x minus alpha n, let's say split, this is the splitting over sigma here. Splitting of h, by the way. Now, what does sigma look like? We haven't really said anything about what it looks like. Well, we know, we've got our theorem from before, the splitting field, I still need to say a splitting field. A splitting field can be obtained by adjoining all of the roots of the polynomial to the base field, the field of coefficients. All right, so in this case, k. So since sigma is equal to, so that's going to be k adjoin alpha 1 up through alpha n, which, by the way, is k adjoin alpha 1 adjoin alpha 2 up through alpha n. We have that have what? That sigma? Oh yeah, sigma is a splitting field for h over k adjoin alpha 1. Now what have we been trying to do? Remember, we're doing induction right now. And so now what we have is we have a polynomial of degree n minus 1. Got our splitting field here. And so, so let me say it like this. So note that the degree of h equals n minus 1, and I of h splits over L. Okay, so now we can apply the inductive hypothesis. So, oh, and I guess I should say, I mean, so why is this true? Well, it's because F splits over L, so of course, or I of F splits over L. So of course, I of H, this remnant right here, has to split over L as well. So now, by the inductive hypothesis, what do we know? There's an extension. So there exists an extension J of, oh, and let's say where it goes from. So J from sigma to L, but this is an extension of, remember that mapping J1. Okay, so now, J restricted to K, that's equal to J1 restricted to K, right? And that is equal to I. In other words, what do we have? Right? Yeah, fine. J is an extension of J1, but if you look here, it's also then, because J1 is an extension of I, J is an extension of I. Right? So that's exactly what we need. By induction, okay, fine, let's write a concluding sentence. So by induction. The result holds for all n. Let me do one. There's a couple of consequences of this, but I think I'll do. Let me see what we got here. Time-wise. Yeah, let's do one of the consequences. So let me do one of the corollaries to this theorem. So this would be corollary 2.8. So let's let I from K to K prime be an isomorphism. And then let's take a polynomial in K bracket X. So and let F be in K bracket X. Now, okay, so now we're going to have two polynomials running around, right? We're going to have F. We're also going to have I of F. And so I want to look at the splitting fields, sigma and sigma prime, for F and I of F. So if sigma and sigma prime are splitting fields, for F over K and I of F over I of K, which is K prime, respectively, then what? Okay, so then there is is an isomorphism. J from sigma to sigma prime, that's an extension of i's, right? So such that j restricted to restricted to k is equal to I. And this is going to be one of our first, we proved these extension theorems. If certain conditions hold, then you can extend your function from one, from k to something bigger, right? And so this is going to be the first time where we actually apply one of these theorems now. So, so for the proof, since k prime is contained in sigma prime, right, we can think of I then as a monomorphism from k into sigma prime, right? So we can, or we have a monomorphism I from k into sigma prime. Now, since I of f splits over splits over sigma prime, there exists an extension j. This is our previous theorem, right? This is theorem 2.7. J from sigma, that's a comma there, so this is from sigma into sigma prime, so an extension j of little I. All right, so here's make a note here. This is theorem 2.7. Okay, so what do we have now? Well, it's an extension, so this is automatically going to be a monomorphism, and so all we need to do is show that it's onto. So it suffices, or it remains, to show that J is onto. And so to do this, well, first what I want to do is I'm going to write out what F looks like. We know that F splits in sigma. So let's write F equal to C x minus alpha 1 up through x minus alpha n, where C is in K and all the alpha i's are in sigma. So now, when I look at I of F, because of this extension, I could use J to apply it, and then we get to apply J to all the alphas. So, so then I of F equals J of F, which equals, now I can apply it in split form, and so this is I of C x minus J of alpha 1 dot up through x minus J of alpha n. Sorry, I'm almost out of room there. But where does this live? This lives in sigma prime bracket x. Sorry, it's a little bit crowded there, but when you apply I to F, or sorry, I should say it better, when you apply J to F, you can apply J to each of the roots. And then, then this has to live in sigma prime of x, which means that J of each of these alpha i's lives in sigma. And so, let's do it over here. Or it follows that, so let's see, sigma prime, who's that going to be? Well, how do you get the splitting field? I keep saying the. How do you get a splitting field? You take the field of coefficients, which in this case is going to be k prime, and adjoin the roots. Well, who are the roots going to be in this case? Well, we can see it's split right here, so it's j of alpha 1 up through j of alpha n. So, so sigma prime is equal to k prime adjoin j of alpha 1 up through j of alpha n. This definitely lives inside the image of J. But then the image of J, let's see, J goes into sigma prime, so this is contained in sigma prime. What does that tell us? Well, this smashes everything together. In particular, it tells us that the image of J has to equal sigma prime. So we can say, therefore, the image of J is equal to sigma prime. In other words, J is onto. That's what we needed, so that finishes off the proof. Okay, so there we go. And I think that's enough for today. That was some sort of hard, intricate work, especially on that proof. I don't know, that one just makes my head swim when I try to do it, so or when I work through that one. So we'll stop here and we'll see you next time.